Hello, everyone, and thank you for joining this session. My name is Ancilia Dmello, and I work for Ford Motor Company. My main focus is on taking machine learning from lab into reliable production system at enterprise scale. Today, I want to talk about a journey many of you are on, moving from experimentation to enterprise by building scalable, observable MLOps systems on GCP. Over the past few years, we have all seen the same pattern. Teams can train impressive models in notebooks or in isolated POC. But when it comes time to run those models reliably in production 24 by 7 under real business constraint, things get much harder. The promise of ML driven insights often collide with harsh operational realities. In this talk, I will walk through the key production ML challenges that block enterprise value, practical end to end ML ops framework on Google Cloud, how we use managed GCP services like Vertex AI, Dataflow, Cloud Run, Cloud Monitoring, and BigQuery, deployment patterns, observability, foundation, and governance practices that make ML systems reliable at scale. My goal is that you leave with a mental blueprint you can adapt in your organization, whether you are just starting with MLOps or trying to standardize around a more robust pattern. The production ML challenge. Let's start with a reality many of us live in. Production ML is hard. On this slide, I am highlighting the core problem, moving machine learning from experimentation into reliable, large scale production remains one of the most critical challenges organizations face today. We can build a great model, but the infrastructure is complex, tooling is fragmented, models degrade silently, governance requirements keep getting stricter. I like to think of it this way. In the lab, the model is a star. In production, the system is a star. You are no longer optimizing just for the model accuracy, but for availability, latency, cost, auditability, and the ability to evolve safely over time. If we do not address these operational realities, the business will not feel sustained, and the value for the ML initiatives, no matter how good your offline matrix look, not be sufficed. So let's break down the main barriers. Core barriers. On this slide, four core barriers that repeatedly show up when enterprise try to operationalize machine learning. First, infrastructure complexity. We are managing distributed system, orchestrating workflows, and maintaining compute resources across development and production environments. It is easy to end up with bespoke clusters, handcrafted pipelines, and snowflake deployments that are fragile and hard to debug. Second, fragmented tooling. Many teams are stitching together different tools for training, deployment, monitoring, and governance, often with every weak integration between them. The result is duplicated work, inconsistent practices, and systems that are difficult to observe end to end. Third, model degradation. Data drift, concept drift, and feature skew silently erode model performance over time. You might ship a model that looks greatly initially, but 6 months later, your input distribution labels and your user behavior has shifted, and your business KPIs start to suffer. Finally, governance requirements. Most enterprises must meet compliance mandates, ensure auditability, and implement human oversight while still maintaining enough operational velocity to ship improvements. Regulations around privacy, fairness, and safety are only increasing, and our ML system must be able to prove what they did, when, and why. The framework I will present is designed specifically to address these four barriers in a cohesive way. a production grade MLOps framework on GCP. Now let's look at the high level framework. This talks cohesive end-to-end system built on GCP platform and addresses these challenges heads on. The central idea here is instead of building everything from scratch, we compose managed services into an integrated architecture that gives us scalability, ability, and governance out of the box. At a high level, the framework covers data ingestion and the feature pipelines, model training and experiment management, deployment patterns for batch, real time, and streaming workloads, production observability for both models and infrastructure, CI/CD driven model deployment, governance, compliance, and human oversight. Each piece is designed to work with others so we can standardize patterns and reduce one off bespoke solutions. In the next few slides, I will walk through the GCP service stack and how it supports this framework. GCP Managed Service Stack. Here you see the core GCP services we use as building blocks. Vertex AI. This is our unified ML platform for training, deploying, and managing models. It gives us built in experiment tracking and pipeline orchestration so data scientists can focus on model logic rather than plumbing. Dataflow. This is a managed service for stream and batch processing. We use it for real time feature computation and for orchestrating data pipelines, which is critical when your models depend on fresh, consistent features. Cloud Run. This is serverless compute for containerized model serving with automatic scaling and pay per use pricing. It lets us deploy inference services that scale up under load and scale down when idle without managing servers. Cloud monitoring. This is our observability platform for metrics, logs, traces, and custom model health indicators across the system. It is a backbone for our dashboard and alerts. BigQuery. This is our serverless data warehouse used for feature engineering, model training data, and prediction logging at petabyte scale. It is also where we do a lot of offline analysis of model performance and the drift. By standardizing on this service stack, we can give teams a clear, opinionated path. You know where to put data, where to train, where to deploy, and where to monitor. This is the clarity that reduces the friction and the acceleration adoption. Deployment patterns, architectural trade off, selecting the right approach. Different workload demand different deployment strategies, and this slide illustrates the key patterns and their trade off. Real time inference priorities, sub-second latency for immediate decision making, fraud detection, recommendation, personalized pricing. Here we care deeply about latency percentiles, availability, and auto scaling behavior. Batch processing optimizes throughout for the offline scoring, nightly, nightly risk scores, weekly churn prediction, monthly flow forecasting. Latency is less critical, but efficiency and reliability at high volume matter a lot. Streaming patterns sit in between balancing real time responsiveness with continuous analysis. For example, continuously updating risk scores at event as events arrive. Your choice depends on business constraints such as latency requirements, prediction volume, cost tolerance, and operational complexity. Each pattern uses GCP services slightly different, but because we keep the same stack, we can reuse governance, observability, and deployment practices across all of them. Let me make this more concrete with a real automotive example, a vehicle oil change prognostics. Traditionally, we change engine oil based on our mileage or time, like every 5,000 miles or 6 months. That rule is simple. but it ignores how the vehicle is actually used. In reality, stop and go, city driving, frequent short trips, or towing a trailer can degrade oil much faster than high highway cruising. With an ML driven prognostic system, we stream telemetry from the vehicle, engine temperature profiles, RPM patterns, trip duration, load condition, driving environment, and historical maintenance outcomes. A model learns to predict the remaining useful life of the oil for each specific vehicle rather than applying one size fits all rule. On Google Cloud, that looks like this data flow ingests and aggregates streaming, sensor data. BigQuery stores historical trips and maintenance records. Vertex AI trains models to predict optimal oil change window. Google Cloud Run hosts the real time inference service that responds when a driver starts a trip. Cloud monitoring tracks both system health and model outputs. So we can see, for example, how many vehicles are being flagged as change oil soon and how this correlates with actual shop visits and engine health. This is a great illustration of why deployment patterns matter. We are streaming data source, real time recommendation to the driver, and batch retraining jobs that periodically refresh the model as new maintenance outcomes arrive. Production Observability Foundation. Now, I want to zoom into observability, which is absolutely critical for production. Without comprehensive observability, production machine learning systems operate in darkness. You might see business KPI degrading and not know if the cause is data drift, a bug in the feature generation, or infrastructure issue or change in user behavior. A robust observability strategy combines model level telemetry and infrastructure level telemetry. On the model side, we monitor things like input distribution, output distribution, and performance against ground truth when labels arrive. On the infrastructure side, we monitor uptime, error rates, latency percentiles, and auto scaling behavior. The goal is complete visibility into system health and performance so we can detect degradation early and respond quickly, ideally before customers notice. In the next two slides, I will separate these two layers, model monitoring and infrastructure telemetry. Model monitoring, detecting model degradation. On this slide, we look at model monitoring techniques we rely on in production. First, data drift detection. We run statistical tests comparing incoming feature distribution against the training baseline to identify population shifts. If the distribution of the key feature shifts significantly, we know our model may be operating out of regime in trained and it was trained on. Second, feature skew analysis. We monitor discrepancies between training and serving feature values. This helps catch pipeline inconsistencies, such as transformation that was applied offline but not online, or a bug introduced in a new feature pipeline. Third, prediction drift tracking. We detect shifts in model output distribution that may signal changing behavior patterns or model staleness. For example, if a classifier's rate suddenly changes, or regresses output range compresses, or explodes, that is a signal worth investigating. Finally, performance degradation monitoring. When label become available, we track metrics like accuracy, precision, recall, and business KPIs against ground truth. This closes the loop and connects model behavior to actual outcome. All of this signal feed into dashboard and alert so the team can respond systematically rather than relying on ad hoc checks or user complaints. If we go back to vehicle oil change prognostics example, model monitoring becomes very tangible. We monitor data drift by watching how the distribution of driving patterns changes over seasons and or between the region. We track prediction drift by looking at the proportion of vehicles flagged for early oil change. If that suddenly spikes in one fleet, it might signal a data issue or model that has gone stale. When vehicles come in for services, we compare the predicted remaining oil life with actual inspection results and feed that label data back into our performance dashboard and retraining pipelines. This kind of feedback loop is what keeps a production prognostic system trustworthy over time instead of slowly degrading into a more expensive version of infrastructure telemetry and system health. Model monitoring is only half the story. The other half is infrastructure level observability surfaces operational issues that degrade user experience regardless of model quality. Using cloud monitoring, we watch metrics such as target availability, uptime, error rates, and service health across all inference endpoints, latency thresholds, response times to ensure we meet SLAs real time workloads, auto scaling efficiency, scaling behavior, resources utilization, and cost optimization opportunities. For example, a spike in P95 latency might indicate cold start, network issues, or contention in shared dependency. By looking at both model and infrastructure telemetry, we can quickly distinguish model is wrong from system is slow and route incidents to the right owners. We saw the value of this setup clearly in oil life prognostics incident. Our operational dashboard suddenly showed that in one region the share of vehicles flagged for change of oil soon had almost doubled, while infrastructure metrics stayed healthy. The daily evaluation pipeline, which joins prediction with service outcomes, confirmed the model had become overly conservative there without improving engine health results. Drift plots revealed that driving patterns had changed due to many new short or that were underrepresented in the training data. We raised an incident, retrained the model on the new data, and rolled it out via our CI CD pipeline. Watching the dashboard as early change, recommendation dropped back to while outcome stayed stable. CI CD driven model deployment. Next, let's talk about how we ship model to production safely and repeatedly. Production machine learning requires the same rigor as software engineering, versioning, and automated testing, progressive rollouts, and quick rollback capabilities. A mature CI CD pipeline ensures every model deployment is reproducible, auditable, and reversible. The deployment pipeline architecture on this slide shows a progressive rollout strategy. A typical flow looks like this: training validation, model fit checks, and cross validation to ensure the candidate model is competitive, automated testing, unit test, integration test, and performance test on the model and the serving code. Canary deployment, releasing a small slice of traffic, often around 5%, and intensive monitoring. Progressive rollouts, expanding to 5 first, then 25, then 50, and then 100 of traffic if health checks remain green. Monitoring and rollback. If we detect degradation, automated rules or on call engineers trigger a fast rollback to previous version. This progressive deployment strategy minimizes risk for exposing new models to increasing traffic volume while continuously monitoring performance. It allows team to move quickly without gambling the entire user experience on each release. Governance, retraining, and human oversight. Finally, we have governance and compliance, which often make or break ML initiatives in regulated environments. Automated retraining pipelines keep models fresh as data distribution evolve. However, regulated environments require human in a loop approval, gates to satisfy compliance mandates, and manage operational risk. In the framework shown here, we see scheduled retraining triggers and automated validation against holdout dataset. For low risk updates that pass all checks, we can auto approve and deploy through our CI CD pipeline. For high risk changes, say models impacting credit decision or safety critical systems, we route approvals to domain expert who review performance, fairness, matrix, and the documentation before promoting the model. Governance controls, auditability, versioning, and rollback. Model versioning. Immutable artifacts with semantic versions linked to training, data, code, and hyperparameters to reproducibility. Governance controls, versioning and rollback. Governance controls support these processes. Model immutable artifacts for semantic version linked to training, data, code, and hyperparameters for reproducibility. Audit logging, comprehensive logs capturing who deployed which model, when, with what approval, and what the outcome was. Instant rollback, one click rollback to previous model version with automated traffic shifting and health verification. Policy and enforcement, automated checks to ensure models meet fairness, privacy, and security requirements before deployment. This control ensure we can not only operate at scale but also answer tough questions for regulators, auditors, and internal stakeholders. Let me close by zooming. This framework provides a comprehensive, battle tested approach to building reliable, maintainable, and observable machine learning system on Google Cloud. By combining managed services with robust observability, governance, and deployment practices, organization can finally bridge the gap between experimental ML and reliable enterprise production. If you are starting on this journey, my suggestion is do not try to be perfect at everything at once. Pick one or two high value use cases, standardize on a small opinionated service stack, and invest early in observability and CI/CD. As those patterns prove successful, scale them out across more teams and domains. Thank you so much for your time and attention today, and thanks for the conference for giving me this chance.